Okay, assignment 1224. One more quick free response assignment. This is obviously a differential equation with slope field. Should recognize that pretty quick. Hopefully you guys kind of like these. I feel like they're pretty predictable, at least in this format. Consider a differential equation. On the axis provided, sketch slope field for the given differential equation at 9 points. They always tell you how many points, so make sure you don't have less than 9 or more than 9. So the first thing I like to do is say, well, where are the slopes 0? So that'd be y equals 1. So 0, 0, 0. So we just got 3 of the 9 points. And then when cosine pi x equals 0, so when does cosine equal 0? At pi over 2 plus pi k. So x equals 1/2 plus 1k. Now that doesn't really help us since we're only drawing slopes at integers. So we're just going to have to plug some other ones in. Plug 0, 0 in. Cosine 0 is 1. Negative 1 squared is 1. So it's positive 1. 1, 0. Cosine of pi is negative 1 times positive 1. If you plug in negative 1, 0. Cosine negative pi is also negative 1 times positive 1. So that one's going to be negative 1. And negative 1, 1. If you plug negative 1 in here, it's going to be negative 2 squared is 4. Negative 4, so it's going to be quite a bit steeper. 0, negative 1, 0 for cosine, that's 1. Negative 2 squared is going to be positive 4, something like that. And 1, negative 1, cosine of pi is negative 1 times positive 4 is negative 1/4. So it's like that. And you can kind of see a little bit of a pattern there. Probably 1 point for the 0 slopes and 1 point for the non-zero slopes. All right, good. Part B, right, just 1 point. There's horizontal line with equation y equals c that satisfies the differential equation. That means it's a solution to it. Find the value of c. Now you can see in the picture right here, it looks like there's a horizontal line there that if you start on, you would end on, and that's y equals 1. So from that, you probably say, well, c equals 1. But let's say it wasn't so clear or you didn't want to do it that way. You could always set your slope. In fact, we already did this. Equal to 0. That'd be a horizontal line, right? And solve for it. Y equals 1. We figured out earlier pi x equals pi over 2 plus pi k. So x equals 1/2 plus 1k. But we're looking for a horizontal line, y equals 1. So there you go. 1 point for that. So that means we have 6 points left for part C. And that's where we're going to find the particular solution. Make sure that you give the domain with your solution to differential equations. So I'm going to rewrite the differential equation just to have it right here handy. So the first thing we've got to do is separate the variables. So y with the dy, use multiplication division to move things from one side to the other. X is with the dx. That's worth 1 point, but if you don't do it, you get 0 out of 6 points. Doesn't matter what you do after that because it doesn't make sense. We're going to integrate both sides. This is power rule, right? This is not natural log. This is y minus 1 to the negative 1 divided by the new exponent. Now there's an inner function. If its derivative gives you anything, then you need to worry about it. It doesn't give you the derivative what's inside the 1. So equals, this is going to be sine of pi x, but chain rule is going to give you an extra pi, so we have to put a 1 over pi in front to cancel it, plus c. So this is probably a point for this antiderivative, point for this antiderivative, point for plus c. If you don't put the plus c, you lose all the rest of the points. Now we have an initial condition, so let's use that right now to find the c. Now I'm going to rewrite this as negative 1 over y minus 1. I'm just going to rewrite it first. I feel like it's going to be easier to work with that. So we're going to plug 0 in for the y and 1 in for the x. Now, sine of pi is 0. So C equals positive 1. So that's another point. So then we're going to rewrite it with the C value in it and try and get the last point by solving for Y and stating the domain. So we could flip both sides and then multiply by -1. And you got to flip the whole side. And then we could add a 1 to both sides. Now, I don't want mixed fractions, so I'm going to multiply top and bottom by pi. So it's going to be -pi over sine of pi x plus pi plus 1. So there's your solution. Now we got to check the domain. Are there any values of x that will cause problems? Well, you got to check this. We don't want division by 0. So we're trying to figure out what the domain is. And we also have to look back at the original derivative and say, are there any issues there? Any values of x that you can't plug in cosine? Y? No problems there. But here, potentially, we don't want division by 0. So we're going to set it equal to 0 and figure out what values of x will cause this bad thing to happen. So then we're going to isolate this. Now, we don't have a calculator, and so you probably don't have this memorized, but this is like -3.14 ... right? And sine has to be between, what are the highest and lowest x, y values? -1 to 1. So this just is not possible. There's no value that makes that happen. So that means we can't mess it up. Domain is all reals, -infinity to infinity. If you don't write that, though, you do not get this last point. So hopefully you guys are getting pretty good at those solving differential equations. We got another problem on the back with some other stuff. So we got a table. So right away you should be thinking, oh, we're going to be using estimation techniques. We're going to approximate the derivative by finding the slope between two nearby points. We're going to approximate the integral by using rectangles or trapezoids. And in a little closer look, you see time, velocity, acceleration. This is probably a one-dimensional motion problem. Car travels a straight track during time interval 0 to 60 seconds. The car's velocity v measured in feet per second, acceleration a measured in feet per second are continuous functions. That might be necessary for some kind of justification or use of some theorem or test. The table above shows selected values of these functions using appropriate units. Explain the meaning of this in terms of the car's motion. So you should know that the absolute value, or the integral of the absolute value of velocity, that's the integral of speed, which is distance. So we're going to say 30 to 60 of the absolute value vt dt is the total distance traveled by the car in feet from time t equals 30 to t equals 60 seconds. You have to have all this. Total distance traveled by the car in feet, time 30 to 60 seconds. Okay? And don't leave that out. Don't say it is. Well, what's it? Be specific. Now, it says approximate it with a trapezoidal approximation, 3 subintervals determined by the table. Now, realize that 30 to 60 is not the whole table. That's just like half of it, right? So 30 to 60 absolute value vt dt is going to be approximately, so I'm gonna draw a little picture here. 30, 35, 50, 60, and we're integrating velocity. So the first one is -14, but we're going to make it +14. The next one is -10, but we're going to make it +10. And the next one is 0, and the next one is 10. Now, we could do So trapezoids connect the endpoints, and we're trying to find that area. These bottom measurements are actually the height of the trapezoids. And you might be like, well, those are triangles. Well, you could treat a triangle like a trapezoid where one of the bases is 0. It works. Try it out. You really need to show work like you're doing trapezoids. This picture is not helping you all. Anything you draw in this picture, don't count on it giving you credit. So we're going to do average of the bases. So 14 plus 10 divided by 2 times the base plus average of the bases, 10 plus 0 divided by 2 times the base plus average of the bases, 0 plus 10 over 2 times 10. Show that work, just to make sure. That's usually a point right there. This is probably a point. This is probably a point, and then your final answer is going to be a point. So we're going to get 24 over 2 is 12. So that's 60. And this is a no-calculus problem. This is going to be 5 times 15. So that's 75. And this is going to be 5 times 10. So that's 50. So we're going to get 110, 185. The units are feet. It's total distance. I like to really label my answers. And it'd be very appropriate to use this wavy equal sign because it's an approximation. So that's probably worth a point there. So that's just part A. Part B says use appropriate units to explain the meaning of the integral of 0 to 30 of AT dt in terms of the car's motion. Find the exact value of it. Okay, so 0 to 30 of AT dt is also the same as 0 to 30 of the derivative of velocity. So you want to think in terms of, well, if you integrate a rate, a derivative, you get the change in the velocity. So I would say that this is not that you have to write this stuff, it is the total change in velocity of the car in, what are the units of velocity? Just look up that table, feet per second from time t equals 0 to t equals 30 seconds. So you need all that stuff. I don't know if you don't necessarily need this, but that kind of helps you figure out what it is you're talking about. Now it says we're going to actually find the exact answer. How are we going to do that without? So, like I just showed you, I actually already showed you the work. This is the integral of velocity. The antiderivative of acceleration is velocity, and then you plug the limits in, and these are values that we can just look up in the table. So these are actually exact. So velocity at 30 is negative 14. Velocity at 0 is negative 20. So that's going to be positive 6 feet per second. So that's a point. That's at least a point. Part C says 0 to 60, must there be a time where the velocity equals negative 5? Justify your answer. Now, when they say that, you're either thinking intermediate value theorem or mean value theorem. Mean value theorem probably comes up more. So we're saying 0 to 60, is it for sure going to go through negative 5? Now, intermediate value theorem says it's going to go through negative 5 right here, right? Because they told you right up here is key. They're continuous functions. It's got to hit negative 5 somewhere in between these because it hits all the values there. That's intermediate value theorem. So we're going to try and write that down. I'm going to say for 0 to 60, there must be time t when velocity equals negative 5. at least once between t equals 35 and t equals 50 seconds. So we're identifying where it's at. Since V35 equals negative 10 and V50 equals 0 and VT is continuous, you guys state the requirements to apply this idea by the intermediate value theorem. Intermediate value theorem. Do not give me initials. Okay, so it's probably a point or two. Point for the answer, point for the justification. Part D, I mean, point-wise, I'm guessing right now on the points. I mean, let's see, I could probably look it up. 2 points, 2 points. 2 points for the first one. Okay, I said 3 points. So say 2 points. 2 points for the second one. 2 points for the third one. So we're up to 3 points for the last one. Oh, 1 point for units on A and B. If you don't put the units, you lost a point. 2 points for the last one. Okay, so D says from 0 to 60, must there be a time where the acceleration equals 0? Now, our first easiest one to defend, the easiest one to explain is if intermediate value theorem. Are there any negatives to positives here? No. That doesn't mean it doesn't go negative anymore. We just can't say for sure. So I think we have to rely on mean value theorem for derivatives. So we're going to try and say, so intermediate value theorem is not going to work. So maybe we could say average acceleration, which would be average v prime. So we could calculate that, and we want it to equal 0. So can you find any velocities that are the same? Because then the average between them would be 0. So I think we're going to focus on these two right here from time 0 to time 25 because they have the same velocity. So the average, when you do a slope between those points, is going to be flat. It's going to be 0. So we're going to say v prime average from v25 to v0. And that gives you negative 20 minus negative 20 over 25 minus 0. It's going to give you 0 over 25. It's going to give you 0. So let's show that work. Let's see. I mean, you could go for the endpoints, but it doesn't work. So, if you know what you're looking for, you can save some time. So that works. So then mean value theorem, since it's continuous, which is a requirement, then we should be able to use mean value theorem. So we're going to say, since VT is continuous and differentiable on 0 to 60, and the average rate of change of the velocity from time t equals 0 to t equals 25 seconds is 0, there must be at least one c value, or c is between 0 and 25, where the actual acceleration will equal the average acceleration by the mean value theorem. So that's kind of what we're looking for right there with the explanation. You gotta talk about mean value theorem. You gotta state the requirements for using mean value theorem. You have to tell me exactly where you got an average value, what it was, and then state then there must be another one, at least one, by the mean value theorem. So that's what we're kind of looking for there. Probably a point for that and a point for your answer and justification. So there you go. So some good review of mean value theorem, intermediate value theorem, integral of absolute value velocities, distance, trapezoids, and some good stuff, table problems. And on the front, we had a differential equation. So there you go.